Hi everyone. Hey, this is just a short movie, the second of two movies on drawing Lewis diagrams, and this one's just focusing on sort of slightly more difficult examples, the sort of ones that we've got on page 25 of the workbook. So if you want to have a look at that while I go through it. And so the first Lewis diagrams we're going to have a look at are those of ions. A little bit more tricky than just your standard molecules. Anyway, same process for all of these, and if you can follow that, you will be on the right track. So as I put in the last movie, this var Bock dt. So that's the process we're going to follow from left to right to draw a Lewis diagram correctly. So the first one we're going to do is the OCl minus, a hypochlorite ion, which is topical at the moment. That's the active ingredient in bleach. And so I'm going to start by adding up the valence electrons. So oxygen has 6, chlorine has 7, and then this whole species has accepted or has an additional electron, making it into an ion. So the way that we represent that, firstly, before we do anything else, is to say that this whole species has a negative charge. It has one more electron than it does proton. So when we counted up our valence electrons and came to 13, we're now adding an extra electron because it's a negative ion. And so we have a total of 14 electrons, 13 from our atoms, and then an additional one due to the negative charge in the ion. So 14 electrons to spread about. So that's the valence electrons part, and then I'm going to the arrangement. And there aren't too many options when you've only got two atoms to use. So I'm going to spread those out, and then I'm going to put a bond between the two to hold them together. I'm going to spread the remaining electrons around the outside atom, and when you've only got two atoms to choose from, you can take your pick. So I've used 2 electrons in the bond, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so I've gone from the outside and central atoms. And now I have used up all of my electrons, and in actual fact, that is the correct Lewis diagram for the hypochlorite ion. And places where people go wrong is that they forget to put the square brackets around the ion and to show that there's a negative charge. They also perhaps forget to add the extra electron, or they may incorrectly take an electron away. Those are some of the common issues. If I just quickly do another one of those ions there, and then you can do the others. But let's say we go for a cation instead. Try the hydronium ion, H3O plus. Starting with our valence electrons, I've got 3 hydrogens, each with an electron, and an oxygen with 6, gives us 9 electrons. And then I also have a positive charge on the ion. Whoa, that's a pretty untidy arrow. I have a positive charge here. So the positive charge means that whole species has one more proton than electrons. So the electrons have been reduced. It's lost an electron and now only has 8. Then I'm going to represent that overall charge with the square brackets. I'm going to arrange my atoms and I'm going to stick a bond between them. That's used up 6 of my electrons. I'm going to check those outside atoms. Well, they're all hydrogen and they all have 2 electrons, so it's happy. I'm going to put the remaining electrons around the central atom. And that's now the Lewis diagram for the hydronium ion. So ions are pretty simple. Just the main thing is that you make sure that you chuck them in those square brackets with the charge on the outside. Then we're on to some of the exceptions to what we call our octet rule. So the octet rule represents the fact that we usually around atoms have 8 electrons, hence the oct part, and tet meaning that they are arranged in pairs. So that's an atom with an octet of electrons around it. There are a couple of exceptions to that. One is the reduced octet, which you see in atoms like boron, beryllium, also in aluminium, but particularly boron and beryllium. And you could also consider hydrogen a reduced octet. So something like boron trihydride, which is in your book there. If we count up the valence electrons, boron has 3, hydrogen has 1 each, so that's 3. So we have a total of 6 electrons to spread around. And if I try and do that with boron trihydride, I'll just arrange my, well, what's happening here? Arrange my atoms and chuck a bond, 1, 2, 3, 4, 5, 6. I've now run out of electrons. There are no more to spread around. And in fact, that is the Lewis diagram for boron trihydride, even though boron has only 6 electrons around it, and hence it's a reduced octet. And usually with a reduced octet, it's simply when you get to the end of your species, there just aren't enough electrons to spread around, and so you end up with a reduced octet. The opposite of that is the expanded octet. And so they're the kind of species you see from C onwards in question 4, page 25. So I'm going to start with this one because it's reasonably straightforward, and that's phosphorus pentachloride. So I'm going to, same process, count up the electrons. So I have phosphorus, which has 5 valence electrons. Chlorine has 7. Oops, that's a 7. So 35 in total. So a total of 40 electrons to spread around. I'm going to arrange my atoms, and so I take a bit of a guess, something like that, and chuck a bond between each. 2, 4, 6, 8, 10. Then I'm going to put the remaining electrons around the outside atoms. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 38, 39, 40. Okay, if I have a look at that, all the chlorine atoms are happy. They have the 8 electrons, but if I actually look closely at the phosphorus in the middle and count it up, it has 10 electrons around it. Hence, and that is the correct Lewis diagram for phosphorus pentachloride, but it's an example of an expanded octet. Phosphorus is stable with the 10 electrons around it rather than the usual 8. And so, usually, a bit like the reduced octet, you end up with that situation simply when you can't arrange that number of electrons any other way. So, if I follow through, perhaps one of the harder examples is the triiodide ion that they've put in your book, that one. I'm going to do exactly the same process. 3 iodines, 7 electrons each, 21 electrons. It also has a negative charge. So this is adding together all the things I've talked about in this video. So it has an extra electron. I represent that with square brackets. I'm going to arrange the atoms and chuck a bond between each. So that's 4 electrons. I've got another 18 to go. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then I'm going to chuck the remaining ones, 17, 18, 19, 20. So I've now used up 20 of those, and I've got 2 electrons to go. And there is the only way to put those electrons in there would be to expand the octet, to end up with an atom with more than 8 electrons. There is simply nowhere else to put them. And they will end up going in the center. And so I have 22 electrons now. Those are in 2 pairs. If I look at that central iodine atom, it is in fact surrounded by 10 electrons, hence the expanded octet. So I hope that gives you a bit of an overview of how to draw these things. Perhaps the best way to do it is to just do a whole lot of examples, and the more you do, the more practice you have, the easier it becomes. All right, see you guys soon.